All right, so agenda for this week. Let's finish parallel loaded resonant converter today. I wasn't able to do that last week, but hopefully today we should be able to do that today. And then no homework due this week, no quiz also this week, because you're going to be having midterm on Thursday, right? You have a lab report due this Friday. The experiment is going to be on series loaded resonant, okay? And then and then the lab report is due this coming Friday at 11:59 p.m. Right? So no homework, no quiz this week, but there is a midterm this coming Thursday, an hour midterm. Use the same Zoom login as the lecture. So please, it's a synchronous midterm as well. So please log in as usual for lecture. Open book, open notes, homework solutions, whatever you can use for the test, you're allowed to use. And then it's going to cover chapters 1 through 3, all the way up to and including parallel loaded resonant converter that we're going to finish today. Calculation and conceptual types, 3 to 4 problems. I don't know yet how many. I have not made the exam yet. And then just like in EE411, if you took it last quarter, you're going to scan and upload your test on separate papers to Canvas, right? Any questions on this week's agenda? Okay, if not, let's finish our chapter 3, parallel loaded resonant. You can see it looks similar to series loaded resonant, right? Except you can see the LC tank is not a series tank anymore, but it's parallel with respect to the load. Right, here's our load. Right here, right? This is our load side. So you can see that the tank itself, right, is in parallel with the load. So unlike the previous one, the load is in series with the series tank, but now the load is in parallel with a parallel tank of inductor and capacitor, right? Resonant. Okay. If you want to do the parallel, not parallel, but the isolated version of it, you can just not replace, but connect a transformer across the cap right there, resonant capacitor, right? And then the rest will be the same, right? You have the full bridge, and then the load itself that has this resistor value as to represent the load, right? Now, we can simplify our analysis by getting the equivalent model of our circuit. So instead of analyzing the circuit based on the original circuit right here, I could just I could simplify, or not simplify, but get the equivalent model first of that circuit and then analyze the circuit using that simplified model, right? So here's the simplified model of that circuit, of the original circuit, right? You can see now we have a parallel resonant, right? And the load is in parallel with the resonant capacitor. And let's see, the difference between this one and the previous one is that here we have several modes as well, right? Discontinuous conduction mode, continuous conduction mode number 1, and then continuous conduction mode number 2. And within each mode, you get different state of the circuits, right? And in series loaded resonant, almost all the circuit states are resonant circuits, except for DCM, when none of the device is conducting. That's the only time when the state of the circuit is not resonating. But the rest of the state of the circuits are all resonant converters or resonant circuits, right? CCM1, CCM2, all the states are resonant circuits in the series loaded resonant, right? But here in parallel loaded resonant, the state of the circuits may not be resonant circuits, right? Depending on which device is conducting. Okay? But in terms of determining the sign of the input voltage to the tank, you can see there's also plus minus right there. And we already are familiar with this, right? From series loaded resonant, depending on which device is connected to the tank, that would determine whether or not you have plus or minus, right? On the input to the tank, right? And we can do that real quickly. If T plus is closed, the other ones are off, then the sign of the voltage into the resonant tank would be positive, right? Positive VD/2 if D plus is on. Same thing happens when D plus is conducting. When D plus is conducting, everything else off, then the input to this tank will also be plus VD/2, right? On the other hand, if T minus is conducting or D minus is conducting, then the input to the tank would be minus VD/2. Right? Okay, and the current, as you can see, if you look at the load right here, just from the point of view of the load, right, the current will always flowing downward, right? Okay, even though the way it's connected to the tank could be different, but at least from the point of view of the load itself, if you are the resistor right there, then current is always flowing downward. Why is that? Well, because we have full bridge right here, right? That would make it one way, right? So current cannot flow backward through the resistor because it will be blocked by these diodes. All right. So just like before, we have. We go back to here. So we're going to analyze the circuit in terms of different operating modes, different state of the circuit by using this equivalent model of the circuit. Okay. And just like in series loaded resonant, you have the three different modes. This continuous conduction mode right here, right, where the switching frequency is less than half of the resonant frequency, right? If that happens, if you select the switching frequency of the circuit to be less than half of the resonant frequency, then you're going to end up with this continuous mode that looks whose inductor, resonant inductor, and resonant capacitor voltage and resonant inductor current waveforms will look like this, right? If it's DCM. Again, this happens when you select the switching frequency to be less than half of the resonant frequency. Keep in mind that when you are designing this circuit or using this circuit, then you're going to have to select L and R, right? The resonant inductor and resonant capacitor, the L and R, L and C. Let me drink my water first. You're going to have to select those values, which means the resonant frequency will be fixed, right? So once you selected L and C in the circuit right here, right, L and C, then that will be it, right? You can be stuck with those two values, right? Per given L and C values, then you're going to get a fixed resonant frequency, right? Now, the one thing that you can still play around with is switching frequency, right? So that's something that you can adjust, right, while you're operating the circuit. So if you somehow choose, right, whatever reason you choose switching frequency to be less than half of the resonant frequency, then again, you'll be operating the circuit in DCM. Right? So let's look at the DCM current right here. It does inductor current, right? It looks similar to the SLR, except if you notice, in SLR, you have two different humps, right? The same thing here, but the difference, oh man, I forgot to connect my tablet right here. Let me do that first. But if you look at the sine wave from that inductor current, you can see that the two humps right here and right there, right? The positive and negative, they are coming from the same sine wave. See that? That's the same sine wave, right? And it happens because we allow the sine wave current to swing negative. See that? Unlike series loaded resonant, I don't know if you remember series loaded resonant. In series loaded resonant, the peak of the resonant peak on the positive cycle is different from, is coming from a different resonant sine wave for the negative half cycle. So let me try to draw that here. Oops. Okay. So for SLR, it looks something like this, right? That's the positive resonant, right? The positive resonant has its peak. Let's call it V peak 1, right? And then it will go negative as well. But when it swings negative, right here, the peak right there, call it V peak 2, is not coming from the same sine wave. So if I call this sine wave, sine of omega t, right? Let's call it f of 1t, right? A sine omega t. Then this sine wave right there comes from a different sinusoidal waveform, right? Different peak. So this is going to be peak 1, and this is going to be peak 2, right? And the peak value, which is right here, that's A1, and there's A2, will be determined by the source, right? Remember, we have series loaded resonant, that you have a source to the tank like this, right? And this source right here will be plus minus VD over 2, plus minus V out, right? So depending on which device is connected on the source side and which directions of the current flowing through the tank, that would determine the combined source to the series tank. And that would further on affects the peak value of that sine wave, right? So when it goes into the negative side, you'll have the same circuit, but different source into the tank, right? That's why it will be a different sine wave at a different peak, right? Does that make sense, hopefully? But here, you can see that the same sine wave continues, right, into negative, right? So this is the same function, right? The sine wave is the same function, right? Does that make sense, hopefully? Right, so they are the same sine wave. We are allowing the current continue to, we're allowing the sinusoidal current to continue to swing negative, right? The same sine wave function to swing negative. And that would create the transition in the switching in the circuit state, right? So here, just go through this. For the DCM, the top waveform, just like in SLR, the top waveform is capacitor, resonant capacitor voltage waveform. And then the bottom waveform is resonant inductor current waveform, right? And now you see why this is called discontinuous conduction mode, because you see the 0 segment right there, right? The inductor current fully discharges and then it stops, right? Before we turn on the other switch, right? So we allow the inductor current to go to 0 and stay at 0 until the next time we turn the other switch on, right? And just like before, I indicate which device is conducting at different segment of time, right there, right? So T plus, D plus, and then none. So during this 0 segment current right there, none is conducting, and then we turn on T minus right there at that point, and this is where we have the freedom of choosing switching frequency. Remember what I said earlier about switching frequency, right? This is something that you can choose, right? That you can still play around with, and that corresponds to moving this point, right? If you move this point right there to the right, that means switching period is longer, right? The switching period is longer, that means switching frequency is smaller, right? And you can see that there is a limit for you to limit on how much or how fast, how high switching frequency you can choose, right? Imagine if you keep shifting this point to the left, right, instead of to the right. To the right, there is no limit, but to the left, look at to the left, right? You can only shift it all the way up to, or down, I should say, all the way down to that point, right? Right there. And that's called boundary conduction mode, right? If let's say I call this point x1, I call that x2, right? If x1 meets x2, that means you have boundary conduction mode, right? If you shift the point x1 more to the left beyond x2, then you will no longer have DCM for this circuit. It's going to be CCM, right? It's going to be CCM1, right? And then if you even shift x1 further down to the left, then you're going to end up with CCM number 2. Right? Okay. Let me erase this. So you can see that. Yeah, go ahead.
I had a question of what you meant by the single waveform versus the two waveforms, because it looks like it's still switching from the switch to the diode. So how is this one waveform and the other two?
Yeah, because you can see, I don't know if you can see, I don't think you could here. The reason being, if you look at the state of the circuit, it can only be explained from the state of the circuit, right? If you look at the state of the circuit from this point, I'm gonna do that, from that point to that point, right? Look at the state of the circuit. Is this circuit right here? Is the same circuit, right? So the circuit doesn't change to a different state at that point. That's why the sine wave that is being created is going to be the same sine wave because it's coming from the same circuit.
Got it.
Whereas the other one, if you look at SLR, oh, let me do this, because you'll see from the state of the circuit. Oh, they're coming from two different states. But, well, I just...
That makes sense.
That doesn't make sense? Oh, yeah, I want to look for the circuits. Yeah,
Thank
so
you.
for SLR, the positive cycle has a different resonance circuit than the negative cycle. Here, you have the same circuit. That's why you end up with the same sine wave for positive and negative cycle. Any other questions? Oops. Okay, let's erase this. So you can see the different state of the circuit in DCM from this right here. This is the part that I don't think I have for SLR under DCM. I did have for, those circuits for CCM1 and CCM2 for SLR. I need to add those for future notes. But here you can see that from this point to that point, for example, right? Even though T plus is already on, but it's not really conducting current. Oh, sorry, it is conducting current. It's conducting current, but you can see that the circuit state is different. Right here, that's not a resonance circuit, right? Because at this point, capacitor voltage is still 0, right? So this is basically no voltage at all, 0 voltage across the cap, and so current through the load will freewheel through the rectifiers right there, right? And then this is exactly the same as zero current switching buck that we talked about a long time ago. And that would force current through this inductor to increase, right? Linearly, right? Because you have voltage across this inductor to be equal to VD over 2. So constant voltage across the inductor means linear increase in the inductor current, right? LDIL dt. And that current will reach I out. Eventually, when it reaches I out, then that would start charging this cap, right? Because it cannot flow through this diode, right? Because remember, diode is pointing up. So that's when IL right there, that's when IL is equal to I out, right? So when IL is equal to I out, then the circuit state changes to a resonance circuit. That's a resonance circuit, right? If you would like to know why, you can go back to the beginning of the chapter. One of the resonance circuit looks exactly like that, right? Meaning what? meaning the inductor current waveform will be sine wave, and capacitor voltage will also be a sine wave. That's what you see here, right? Right after IL is equal to I out, right away the capacitor voltage resonates, as well as inductor current start to resonate right there. So now both are sine wave, right? Until inductor current reaches zero, right? And then when the inductor current reaches zero, then we have none of the devices conducting. So right here, so the circuit state changes to this one, right? And then you can see if none of the device conducting, then we are allowing the capacitor to fully discharge with a constant current I out, right there. Remember, IL is already zero, right there, right? IL is already reaching zero. So no more charge through IL, therefore no more current, and then the device is not conducting anyways, none of the device conducting, that's why it's open. And then this I out, right, will have to flow through capacitor voltage, resonant capacitor, because at the time, capacitor is still not fully discharged, right there. See that? So capacitor is not fully discharged, so therefore, this forces the output current to flow through the cap and discharging this capacitor with constant current, which means the rate of the discharging voltage on that capacitor will be linear, not sine wave. So that's why I put linear right there, right? dV/dt is equal to I out over C, right? So that's why it's constant rate, decreasing voltage, right? Until when? Well, until capacitor voltage goes to zero, but until we deplete all the energy inside the capacitor, at which time capacitor voltage becomes zero, and that would turn on the diode, right? Diode across it. So as soon as capacitor voltage equals to zero, right, then the capacitor, the diodes that are parallel to it are ready to conduct current, forward bias basically, right? And that's when the circuit transitions to the next one. When current now flows through, output current flows through rectifier diodes, right? And it keeps freewheeling through these diodes until when? Until we turn on T plus again. So the cycle continues, right, or returns. All right, any questions on this? So you can see that this is different from SLR in a way that not every state is a resonant circuit, right? In fact, there's only one resonant circuit out of these 4 states, right? Which is this one right here. Oh, sorry. That's the only resonant circuit out of the 4 states. Okay. In SLR, you have 5 different states in DCM. 4 are resonant and 1 is not. But here you have 4 states with 1 being resonant, the other 3 are not. Any questions? Okay, if not, let's look at, let me ask you the question, the same question I asked for SLR. Can I use, by looking at the timing on when the switch is turned on and turned off, and then diode is turning on and turning off, right? By looking at these waveforms, especially the inductor current, can you tell me whether or not we can use, a thyristor for this mode? Remember, thyristor is semi-controllable switch. Can we?
Looks like it.
Why? What is the reason?
Because you naturally shut the switch off when the current through the switch is zero.
That's correct, exactly. Since the switch, very good, since the switch turns off naturally at zero anyways, right? We don't have to force it to turn off right there. Therefore, we don't need to force the switch to turn off. Well, that means semi-controllable, right? Because if you have a semi-controllable switch, you are able to tell the switch when to turn on, but not to turn off. In other words, if you have a semi-controllable switch, the switch will turn off naturally at 0 amps. And that is a perfect condition right here to use a semi-controllable switch, right? Because the switch turns off at 0 amps naturally, following a sine wave, right? Can I use a slower diode than Schottky's for this mode?
I think so, yeah.
What's the reason?
From my perspective, when D plus and D minus are turning off, you have zero current after.
Yes.
So it doesn't, the turn off downtime doesn't matter as much.
Right. And in other words, very good. You are not forcing the diode to turn off, right? It will go to zero. Its current will go to zero and naturally it will turn off, right? Because current through the diode cannot reverse its direction, right? So you can see that because the diode current, which is in this case the same as the inductor current, naturally goes to zero, right? Therefore, the diode turns off at zero current, right? Naturally, we're not forcing it, right? So therefore, since it is naturally going to zero when it's turning off, right? And right when the diode is turning off, the current through the diode is 0 amps. Therefore, there's not much reverse recovery that the diode has to do, right? Because it's 0 amps to begin with, right? It's not turning off at some high current. It's turning off at 0 current. So therefore, the reverse recovery time will be very fast because of the 0 current when it's turning off. That's the reason why you could use a slower diode in this case. It doesn't have to be a Schottky, which is a good thing, right? Because this converter is typically used for high power, high voltage, right? So if you are dealing with high voltage converter, then it would be nice to be able to use high voltage components, right? And Schottky's, I mentioned this last week, the highest rating I've seen is 250 volts. Maybe they can go up higher than that these days, but 250 volts is kind of like the max for Schottky's. Right. So what if you are using this circuit for 10,000 volts, 20,000 volts? Right. Then you can use PN junction, and PN junction diode can go up really high in terms of voltage rating, right? So that's a benefit that you can get out of this mode. Number one, you can do semi-controllable switch. Number two, you could also use a slower diode. The same thing with semi-controllable switch. The voltage rating and the current rating of semi-controllable switch is much, much higher than controllable switch, such as MOSFETs and IGBTs. Right? Thyristors can go up to thousands of volts, thousands of amps, whereas MOSFETs and IGBTs, they can only go up to a low, several thousand volts ratings. And not much current as well, relatively speaking, compared to thyristors. All right. What else I can ask from here? Oh, yes. Now, table. The soft switching characteristics of this board. Let's say I have 0 current switching, 0 voltage switching, I turn on, I turn off, right? All right, and I'm gonna need the circuit for this. So just like series loaded resonant, I'm expecting you to know how to fill out these tables and reasons behind why it is a yes or a no, right? So let's start with ZCS at turn on. Who wants to volunteer? Or should I call? Who wants to volunteer? 0 current switching at turn on, is that a yes or a no right here?
Yes.
Yes, why?
So on the T positive, the sine wave is going towards 0, and then on the on the T negative, the sine wave is going towards 0, and then on the T positive, we can see it's flat at 0.
Right. Well, because it's sine, yeah, very good. Because it's following the sine wave, right? Right here, for example. So if you approach current of that switch from the left, T0 minus, that's going to be 0 amps because it's off anyways, right? So approaching from the left, it's 0 amps. Approaching from the right, right? So if you approach from the right into this point, T0, let's say, eventually it's going to go to 0 because it follows the sine wave, right? As you are approaching or tracing the sine wave to the, not to the right, sorry, to the left, oh my gosh, to the left, right there, right? If you follow the sine wave to the left into T0, you can see eventually we'll reach 0, right? So if you zoom in to what happens right after T0 or T0 plus, you will also see 0 amps. Very good, Giselle. So it is a yes. Anybody disagree with that? All right. How about at zero current switching at turn off? I want a different name. Who wants to volunteer?
It would be a yes.
Why?
Right. Because at T0 plus and T0 minus, you have 0 amps flowing through.
Why is it that at T0 plus is 0?
Looking at the graph, the inductor's current is the same as the switch's current, and you have that little flat line after, which is at 0, and then you have a sinusoid before, which is basically 0.
Yeah, very good, Nick. So yeah, T0 plus, that means right after we turn off the switch, right? So if I call this the T0, right, for turning off, then right after it's going to be flat, right? Because it's going to be off anyways, right after we turn off. So we know that T0 plus must be 0 amps. So that's the easy part. T0 minus, as you can see, right, inductor current is the same as the switch current for this time segment. You can see that it follows a sine wave, right? So eventually it will approach 0, right? So that's from the left side going to the right. Eventually it's going to be 0 amps. Right before we turn off the switch, it reaches 0 amps almost, right? So therefore it is also a yes. Very good. All right. 0 voltage switching at turn on. Let's do it turn off first. 0 voltage switching at turn off. Okay. I need a volunteer. Before I call. Eeny, meeny, miny, mo. Who wants to go? No volunteer? All right, I'm gonna call. Who's the lucky person? Let's see. Oh, how about you, Jenny? I see your name on here.
It was ZPX off. On.
Turn off, right here.
I think it's a yes.
It's a yes. Okay, why?
Wait. Sorry, where's the point again? It was when T minus turns off, right? So in between T minus and D minus.
Yeah, so you need to look at when we turn off the switch, right? Right here. This is when we turn off the switch. So call that T0. So what happened with the voltage across the switch at T0 minus and at T0 plus? How many volts? How much volts?
So when the switch is conducting, there's 0 volts across.
Okay, so which one is that?
0 minus.
T0 minus 0, okay, very good. What about T0 plus?
That's when the diode turns on, so that's also 0 volts because it's in parallel.
Okay, good. Yeah, I was gonna ask you on that one because there are 2 diodes, right? So yeah. Specifically, the diode that is across that switch, the one that you're turning off, is taking over the current. For example, right there, you see that D plus. The next one that's going to turn on is D plus, and D plus happens to be across T plus, right? So if D plus is conducting right after T plus, that means voltage across D plus is 0, which also means voltage across T plus after it's turning off is also 0, right? So therefore, 0 and 0, that gives you a yes. Very good. I'm just gonna try to remember who's in the class. Let's see. Andrew, what voltage then you have at the other switch, T minus? I'm still referring to this mode right there. Or that.
Still for turn off?
Yeah.
Okay.
Zero voltage switching at turn off, which is a yes, right? So let's say that you're turning off T plus, right? Let's just say. What is the voltage across T minus after you turn off T plus? Let's say this one, during that time, when D plus is conducting. What is the voltage across T minus?
Shouldn't it, so T plus is conducting, D minus is not conducting, T minus is off, so shouldn't it be positive VD over 2 or is it negative?
Okay,
Okay.
take your pick.
Okay, I think it's positive VD over 2.
Okay. Now, answer the question again by looking at this circuit. Maybe it helps. Right now, D plus is conducting, right? D plus is conducting.
Okay.
So my question is, what is the voltage across here?
Oh, is it VD?
There you go.
Because
Yes.
it's the
Yes.
both of them. Oh, okay.
All right. So it's always, I think it's always helpful to go back to the circuit to determine what, the amount of voltage corresponding to a different device, right? If you are asked that kind of question, right? Depending on which one is conducting, right? So now you got the answer. That's going to be VD. Very good. Okay, the rest of the class is clear, right? Why this is VD? Because if that diode D plus is conducting, that means it's 0 volts across. That means 0 volts across here, right? And then by KVL around this loop, right, you can see that voltage across T minus got to be the total voltage, right? Plus VD over 2, plus VD over 2, that's VD. Okay? Any question on this? If not, the last one. Who wants to volunteer or should I call? Right here, the very last one.
I think it's no. Because
So no?
Yeah, for T0 minus, you have no current across the switch or the diode, so they're both off. So the voltage across them would be VD over 2.
Okay. Sorry, say it again, Fabian, right? Let me do this. Let me erase this. Okay, let's take a look at where T0 is. We are turning on the switch, so the T0 point is going to be different. So let's say you can pick this one, right? That's one example of T0, or maybe this one. That's our T0 right there. So what did you say, Fabian? At T0 minus?
Yeah, T0 minus, you have no current across the switch or the diode, so they're both like open. So that means that the voltage across the switch would be VD over 2 at T0 minus.
Okay. And then at T0 plus?
The switch is conducting, so that would be 0 volts.
Very good. So you can see by just looking at these two values, right? Let's say I draw T0 right here. That's our T0 point. Right before T0, it is very high, right? VD over 2. And then right after T0, voltage is 0, right? So it jumps from very high voltage and drops to 0 in almost no time, right? So that's a hard switching, right? It's not soft switching anymore. When voltage jumps or current jumps like that, right, from high to 0 or from 0 to high, that means it is not soft switching, right? So the answer is correct. It's a no. Good job. All right. Okay. That will be it. The other two, I'm gonna let you look at them yourself. I think you should be able to figure out the soft switching characteristics of parallel loaded resonant. What happened? Parallel loaded resonant at DCM and at CCM1. Where's CCM1? sorry guys, let's see, CCM1, that's DCM. With different states, right? And then that's the table, right? And then here's CCM1 right there, right? You can see now it's looking more like a sine wave, right? Still not that pretty, but you know, at least it's better than DCM, right? DCM is the waveform is just very distorted, right? So you can see the quality of the sine wave is better here, right, with CCM1. And in CCM1, take a look at the states. All four, now we have 4 states, not 5. Oh wait, before it was 4 as well, right? 4 states, and all 4 are resonant. See that? So this is a resonant circuit, and that is also a resonant circuit. The third one is also a resonant circuit, and the last one is a resonant circuit. Right? And you can see it's always sine wave. See, look at the waveform, look at the inductor current as well as voltage, but just focus on the inductor current. It is always a sine wave. See that? Anytime it goes into a different state of the circuit, it's always a sine wave. Sine wave. There's no linear here. It's always a sine wave. Right. Okay, and how do you get to this mode, CCM1? When switching frequency is selected to be between half of the resonant frequency and the full resonant frequency. So if you select your switching frequency for the circuit to be between this range, then between these 2 values, then you get CCM1, right? And looking at which device is conducting, right? You should be able to determine which soft switching is provided at 0 voltage, at 0 current, right? And you can fill out this table right there, right? Yeah, make sure that you do this, okay? And then if, let's say that you get different answers than mine, then let me know, and stop by my office hours and let me know. Same thing with the last one right here, CCM2. You have the table that you need to practice, right? Soft switching characteristics. And have a look at the quality of the sine wave here. It's even better, right? Look at the inductor current. It's almost like a perfect sine wave there, right? And why is this important to emphasize? Just like SLR, right? When we estimate the output voltage, we are using a sine wave approach. Right? That's why the closer the sine waves, the closer the waveforms in the circuit to a sine wave, the better estimation you'll get for the average output voltage, right? So the equation that we derived last time for SLR, that's going to be more accurate for CCM2. It's going to be the least accurate for DCM. Again, by looking at the quality of the sine waves, right? Okay, so please again go through this discussion on determining the switching characteristics, this table right here, right? For CCM2, again, if you get this different answer, then let me know. Okay? If you are still confused on how to, or not understanding how to determine this, then let me know. Stop by. Average output equation, same as SLR. We are using sine wave approach. Right? So we are right there. We are using a sine wave approach, sine wave method from square wave. Right? I call it square wave method, but the reason being, the input is going to be flipping back and forth between plus VD to minus VD over 2, and the output is going to be either plus or minus I out. And from that square wave, we just take the first component, fundamental component of the Fourier components of a square wave, right? As you know, a square wave, you could derive the Fourier components of that square wave, right? Which is basically a series of a sine wave functions, right? And we are only looking at or considering only the first component of these Fourier components of a square wave. Right? So that's why you see, just like in SLR, you see the subscript, right? 1. It means we only look at component number 1 in Fourier series of a square wave. Okay. Now, the average output, not the average, sorry, the capacitor voltage, the resonant capacitor voltage, as you see earlier, right, is sine wave, right, or it follows sine wave. And if you operate in CCM/2, it's almost like a perfect sine wave. And then it goes into a bridge, right here. So this is going to be a sine wave voltage across the cap, right? It will be more sine wave if you operate the system in CCM2. And that sine wave voltage will be rectified by this bridge, right? You rectified, and then you have this filter capacitor to give you almost flat, right, across this load, right? So basically you are rectifying a sine wave, right? And you, as you learn from EE411, the average voltage across a rectified sine wave is equal to 2 times the peak value of the sine wave divided by pi, right? So that's from EE411, 2 times V peak divided by pi, right? And again, we only consider the fundamental component, or component number 1 of the Fourier series in the square wave. And then the current, same way, the current IB prime B1, right? We only look at the fundamental component of that current, and the peak of that component is 4 times I out over pi, right? That's for a square wave. So again, the amplitude of fundamental frequencies of the square wave output current is 4 times I out over pi. Right. So from here, I can solve for the equivalent resistance, right, of the equivalent model that we want to estimate the output voltage from, and that is related to the actual load resistance R, right, by this constant right here. Right. And then VAB1, that's the source into the tank. Since we have a half bridge, that's going to be 4 times, and this is again from square wave, 4 times the peak value of the square wave divided by pi, right? So now we have our equivalent circuit, sine wave equivalent circuit, right? The sine model, sinusoidal model of our circuit, right? Where the input to the tank is plus minus VAB, VAB1, right? And VAB equation is given previously, and the resistor, the load resistor, is reflected into this model to be RE. Right? So it's not the same as RL, it's RE, and you have the equation for RE, right, with respect to RL, the actual load resistor. Right? Okay, so that's the value that you will put there. Now, our interest is to be able to find output voltage, right? And our output voltage is right here. That's our output voltage, which is the same as VC1 right there, right? So how do you get output voltage from the circuit? Well, if you have the input voltage right here, output voltage right there, then I could use voltage divider, right? I could use voltage division to get the output voltage, right? Voltage across the resistor, it's going to be a fraction of voltage source right there, right? That's what that's how I derive the output voltage equation right here. That VC1 is going to be a fraction of VAB1 right there, right? And it's going to be a long algebra because you have parallel combination and in series with the L, right? And at the end you get, oh, it's a long derivation. I remember deriving this. And at the end you get this equation right there, right? Okay, that would allow you to estimate average output voltage in terms of the input voltage, right, VD. And then, of course, XL, XC, those are related to the resonant inductor, right? That's reactance of the inductance. And X of C is the reactance of the capacitor, right? And R of E is the equivalent resistor that we already looked at earlier, right? Right, so that's the equation that you can use to estimate the average output voltage of the circuit, right? Again, given L and C. As I said earlier, when you are designing the circuit, you must know what you must select, right? You must choose L and C before you build it. So that will give you XL and XC. And also knowing the load resistance, then you can know equivalent resistance that you put here. And of course, you would also know input voltage that you would plug in there. Okay. And here, these are the equations for reactances, as you already learned from circuits class. Any questions on this? So again, this is just an estimation, right, using sinusoidal approach. Right? We're only considering the first component in the Fourier series of the square wave. And that's why earlier I have emphasized the shape of the waveforms, right? So I'll say it one more time that this equation will be more accurate for CCM2, and it's going to be the least accurate for PCM, right? Why? Because of the shape of the waveforms, right? The more sinusoidal the waveforms are, the better estimation you get from this equation, okay? Now, in addition to using this equation, I could also use graphical method to get or to estimate the output voltage, right? Since we have L and C, therefore we can associate those two energy storage components with quality factor U. Right? So that's what I'm going to do here. I'm going to plot family of curves, right, per given quality factor, depending on how much resistance, how much capacitance, and how much load resistor you have. That will determine the quality factor, right? And make the long story short, I rewrite the equation in terms of quality factor, as well as in terms of the ratio of switching to resonant frequency. Again, this is I didn't show the what do you call it, the entire steps, but I derived this equation, and at the end, if you do that, if you express the same equation that you have earlier, right, and then substitute the values here, x of L, x of C, and R of E in terms of Q and ratio of the switching frequencies, then you get the new equation. And here's how to substitute x of L and x of C in terms of Q and ratio of the frequency. See that? So right there, you just plug in x of L in this equation with this equation right here, right? And then x of C with this equation right here. Okay. All right, if you do that, then at the end you get a new equation right there that shows the relationship between the ratio of the voltages, output over input, right, in terms of Q, and the ratio of the frequencies right there, right? So in order to graph this, I'm going to assume a constant value of Q. So for a given constant value of Q, I can graph the ratio of the voltages with respect to the ratio of the frequency. Now, why is this good to have? Well, because this ratio of the frequency determines the operating mode of the converter, right? Remember, below, what is it, half of the resonant frequency, you're going to get DCM, right? Higher than that, you get CCM, right? So this determines the operating mode of the converter, that ratio. All right, so then you can see we have different family of curves, right? For Q equals to 1, 2, 3, 4, 5. I just included 5 graphs for 5 different values of Q. Okay, so per given Q, if you know the ratio of the frequencies, then you will know the ratio of the output, the ratio of the voltages, right? By using this graph. Any questions?
Professor, this doesn't account for any like reduction you set up in the transformer on that output, right? This is just if it was a 1-to-1.
Yes, very good point. Very good point. You're right. This is this doesn't take into account transformer turns ratio. You're right. Right.
I have like a side note kind of question on the transformer. Like just for the final project, I was looking around for like transformers. Can you just use any like kind of transformer, or are you looking for something kind of special?
Well, low frequency transformer is different from high frequency transformers. So for this type of application, you definitely want to look for high frequency transformers. Because typically you would operate these at higher than 60 hertz, right? At least kilohertz type of switching frequency, right? So
Is
you
that
need,
something
go
like
ahead.
find on DigiKey by like just searching high frequency transformer?
Now, you'd have to go to the transformers and then use the drop downs and set your core material probably. And then there should also be some Q factor stuff for certain frequencies that you want to go through.
Oh, I gotcha. And you look at
DigiKey's bad at like
research the
parsing.
high-
Yeah, it's bad at parsing just like search terms.
Yeah.
I've spent a lot of time digging for components on DigiKey. Like the menus are where it's at.
Okay, yeah, I'm having trouble with DigiKey, so
Yeah,
that's why I
yeah.
asked.
Exactly. So yeah, they especially made transformers, for high frequency transformer applications. Different core sometimes, different ways of connecting the wires, right? Yeah, different materials of the cores. So yeah, so high frequency transformers basically what you want to use for this type of application. Right? And also depending on the power, right? You will have to look for not only for the frequency range of the transformer, but also the water. Water. Oh my God, I need to drink water. The wattage rating of the transformer. Right. So make sure.
Yeah, I'll
that,
definitely keep that in mind.
yeah. All right. Are there any other questions? All right, if not, let's look at the steady state operating characteristics of PLR. Remember what we got from SLR? Series loaded resonant has a very cool, in my opinion, steady state characteristics in that if you operate series loaded resonant in DCM, then it operates, or it not operates, but it provides or it offers a huge benefit when it comes to short circuit protection, right? So if for whatever reason the load is shorted, right, instead of pulling very large current into the load, it will actually limit the current, right? It has a inherent short circuit protection if you are again using SLR, the previous converter, in discontinuous conduction mode, right? You don't need protection device at all to protect the load from short circuit condition. The converter inherently will protect that. And you'll see that today in the lab. You're going to be simulating a short circuit condition for SLR. And you'll see how cool the circuit actually limits the current without putting any fusing. So it'll limit the fault current basically to a manageable current. Right? So that, to me, that's pretty cool. Here, if you are using PLR, parallel loaded resonant, strictly on the DCM, you can see I'm only providing two different graphs, right? Two different curves. One for output 0.4, the other one is for output current, not output current 0.4, and the other one is output current 0.8. These are all normalized based on the full load current. Right? So different currents basically, right? Different load currents. You can see that the two curves merge again, just like SLR. When you operate the converter in DCM, see that? This is DCM right here. The two curves merge, meaning what? Well, if you, let's say, are running at, let's say 0.25, okay? 0.25 is easy right there. 0.25, right, ratio. So that's the ratio again of switching frequency over resonant frequency right there, right? So if the ratio is 0.25, meaning you're operating in DCM, then it does not matter what current the load is seeing or drawing. It will always give you the same what? The same voltage. See that? So what does it mean then? Well, how is it a benefit? If for different currents you get the same voltage, how would that benefit us? Anybody?
You won't fry the circuit. You won't, in case of a short circuit, because the curve, like if you're not operating in DCM, like each load resistance has its own curve, and let's say you were operating it at like like one, like a ratio of one, then it would like shoot up to like infinity basically. Like it, like as your load resistance goes to 0, but it doesn't matter because the R equals 0 line is the same as any other resistance.
Interesting observation. Unfortunately, what we are seeing now is actually voltage with respect to ratio of the frequencies, not current. I think what you're referring to is, current with respect to frequencies, right?
So like if you short the load, like V out will be like, wouldn't it be infinite current then? Like even at 1 volt and you have a 0 ohm load, like wouldn't it just shoot up to infinity? It would try to maintain that 1 volt.
Yeah, so you will still get infinity though. You will still get infinity current through the load, right? Like this. That's what you're saying, right? Like you got actually it's going to be
or even in DCM too.
Yeah. So what I'm saying is that your current is still infinity, right? Let's just do it this way. Change this to infinity, right? Let's just say that's for infinity, right? Right. That means along this red line is going to be infinity current, yes?
Right.
Right. So at this point, don't you still have infinity current?
Yes.
Exactly. So your load is still seeing infinity, right? That's not going to protect it from short circuit current. The voltage, however, it will still be the same voltage, but the load is still seeing huge current. That's not an advantage. Do you agree?
Oh, so it like regulates it very well.
That's right. That's what I'm getting at. Exactly.
Line regulation.
Voltage regulation. Yes. Voltage regulation.
Wait, load or line regulation? Load, right?
Load regulation. Yes. It's a load regulation. So yeah, so it does not protect it from short circuit protection because you will be seeing the high current still. But what this graph is showing is that it doesn't matter what output current, right? It doesn't matter what load current you're drawing at a BCM. Let's say you operate the circuit at this point, then you always end up with the same output voltage, right? So that's regulation. That's voltage regulation. Now, why is that an advantage? Well, typically, how do you regulate the output voltage of a converter? Typically, what do you do to do that?
Feedback system.
Say it again.
Closed loop system.
Yes,
like
exactly.
a feedback system. Yeah.
You have to have a feedback system. You have to have a controller to regulate the output voltage. Here, right? You don't need any controller to regulate the output voltage. You don't need a feedback system to regulate the output voltage. To me, that's pretty cool, right? That converter can maintain the same output voltage regardless of the output current without using any means of sensing the output voltage, right? I don't know about you, but to me, that's really impressive. That's really interesting, to amazing circuit to have. If let's say you need that kind of not very tight regulation on the output. Of course, in the real world, it will vary a little bit, but at least theoretically, you can see from here that the output voltage stays the same at the same value. Doesn't matter what the output current is, right? Okay. So that's the advantage that you get out of this circuit if you run it at DCM, right? One of the advantages, right? Other advantages you see it from the table, right? Soft switching characteristic in DCM is better than the other modes. Okay. The only thing about DCM is that power quality is bad, right? Because the shape of the waveforms are ugly, right? They're not even close to a sine wave.
Are there ways to improve power quality, like with external circuitry?
Right. So internally, very good point. Internally, the converter has or produced very bad, waveforms. So what can you do to protect the load as well as the source to see these harmonics, basically, right?
Filter out the bad harmonics.
That's correct. Yes, because harmonics are just high frequency components that you should be able to filter out to a certain extent, right? So you block the harmonics at the input with input filters, and you also block the harmonics at the output by putting, harmonic filter on the output, right? Low pass, basically, low pass filter, right? Okay. So basically what I'm saying is that if you are using operating DCM, then the filtering requirement is going to be heavier than CCM1 and CCM2. That's the trade-off of operating in DCM. Any other questions?
Wait, could you use like a switching filter, like a switching active filter?
Yes, you could. You absolutely could. Expensive though, right? Because then you have to do all kinds of sensing. You have to actually do, when you say active harmonic filter, do you mean sensing the frequency content and then add 180 degrees phase shift, right? To that content to cancel.
It's like, a switched capacitor filter, because it's got to handle the power too going through it. Because you can't just put a op amp in it, do like a regular filter like that, because you can't drive like however many watts through it.
Right. Yeah, exactly. So it has to be a power filter, but in order to do active harmonic filter, you're going to have to be able to know the location of the harmonics, number one, right? So number one, location. Number two, phase angle. Because keep in mind that every harmonic is just a component at a certain frequency with its own phase angle, right? So if I do a complex plane like this, right? For example, if the fundamental component is right here, let's just say, right, at that angle, that's the fundamental component, meaning first component of the Fourier series. Then the second component or the third component, let's say the third component, because it's really rare to have even harmonics. Let's say the third component would be, okay. Let's say the third component would be right here. Let's just say smaller, right? V3, and you can see that the third component in the waveform has that magnitude, right? Whatever that magnitude is, and this phase angle right there. So the controller, not the controller, but the sensor for harmonic, active harmonic filters must be able to, number one, as I said, find the location of these harmonics, in this case, 3 times the frequency, and then find the angle, which is this one right here, right? If it can do that, then it will, the sensor then it will generate signal into the power filter, right? It'll inject signal, actively inject signal at 180 degrees apart, the same magnitude. And then you would add, you would add the two. Right?
So that would be like a pretty tough controller.
Expensive, yeah. But it exists. It really exists. These harmonic filters, they call it active harmonic filter. They exist. And they're very expensive, of course. Fancy injection filters, right? But it's clever, right? You just look for the location of the harmonics and add 180 degrees to cancel, right? 0. Okay, any other questions? If not, this is an example for half bridge parallel loaded resonant. Input is 100 volts, and then we have the capacitor and resistor, and then we have the switching frequency, and then the load resistance, right? These are all given. So you already selected the resonant components right there, and then you selected switching frequency in this case, and input voltage as well as load resistance. Determine the output voltage of the converter, assuming the output filter components produce a ripple-free output current and voltage. So here from LC, you get resonant frequency, right? That's from LC. And then you can also get Q. It looks like I'm using graphical method because I'm using Q. That's how I know. I calculate Q, that's equal to 2. And then I already have the omega naught, right? From which I can get F naught, just divided by 2 pi, right? And then I have the switching frequency in kilohertz right there. So now I can get the ratio of switching frequency to resonant frequency. That gives me around 1.2 for the ratio. So then we need to estimate the output voltage. Right, so knowing those points, those values, right, Q is equal to 2, I use MATLAB to generate the curve or the graph at Q equals to 2 right there. Q equals to 2, and then from there I can go to this point 1.2, right, the ratio of the frequencies. So 1.2 is right there, right, and then draw a straight line up until it intersects with the graph, and then straight across to give you the ratio of the voltages, right? V out over VD. Turns out to be what? 0.6 something, 0.6, is it 2 or 1 or something like that? Where do I put? 0.61. So 0.61 roughly. And then since I know what VD is, right, then I should be able to calculate for V out, right? So 0.61 times 100 gives you 61 volts. And looks like I also calculated using the equation that I derived earlier, right here for output voltage. Instead of using graphical method, I use the same information right there and then use the equation to find the output voltage. And if I do that using equation instead of graphical method, I get 60.661. Not bad, right? Right there compared to that, pretty close. Again, these are all just estimations, so you're going to get output voltage of around 60 volts, right? Any question on this? In the exam, I would specify which method you must use. I could say use graphical method, or you must use the equation. If I ask you to use graphical method, then I will provide you with the curve, right? With this curve right here. Okay. Any questions?